If you map out the physical hardware topology of a modern data center, you are looking at an illusion. The physical location of a server no longer dictates how information flows through it. Look at this archival photograph of early computer networks. For decades, networking was defined by copper and routing tables. Making a change meant physically moving a plug. Information was bound by these rigid physical constraints. To understand how modern architecture operates, we are going to freeze time. We will track a single isolated query from the moment a user hits send to the millisecond it is processed by a cloud-hosted artificial intelligence. Following this single data packet exposes three distinct pillars: zero trust security, software-defined networking, and the transformer mathematical kernel. The scale of these systems only becomes visible when we analyze the exact moment our query hits the network's outermost edge. This shift towards software-defined abstraction allows modern LLMs and cloud systems to scale without being restricted by the layout of the physical hardware. Traditional networks relied on implicit trust, often called a castle and moat topology. Once a user crossed the physical perimeter, they were trusted. A single breach of that outer wall granted attackers lateral access to the entire interior. Because physical perimeters proved vulnerable, cloud networks adopted zero-trust architecture. Verification is applied directly to the payload, regardless of location. The mandate is that every request is treated as hostile. It must be cryptographically verified at every step, even inside the network. Implementing this mandate requires breaking security down into a practical framework known as defense in depth. This visual represents defense in depth. The security stack is built out of multiple overlapping checkpoints that operate independently. As our query moves through these layers, each independently verifies confidentiality, integrity, and availability, creating a system without a single point of failure. Security is no longer about protecting a geographic location. It is entirely focused on verifying the unique digital identity of the request itself. Our query successfully clears the final authentication layer, proving its identity, and is handed off to be routing internally. Migrating security from a geographic perimeter to identity-based layers helps isolate threats at the micro level, preventing a single point of entry from compromising the entire system. Once inside, the query needs to find the exact application it is trying to reach. Traditional physical switches cannot scale fast enough to handle millions of dynamic microservice requests across a modern data center. To bypass the limitations of physical hardware, infrastructure engineers developed software-defined networking, or SDN. The core mechanism of SDN relies on decoupling the network control, the control plane, from the physical forwarding nodes at the bottom. This logically centralized intelligence dictates routing paths through software, issuing instructions to the forwarding plane without altering physical connections. Kubernetes operates as the orchestration engine that manages this software-defined model for large-scale applications. In legacy systems, engineers had to manually map specific application ports to rigid virtual machines. This created a bottleneck whenever the application needed to scale. Kubernetes addresses this by abstracting the application workload away from the underlying machine. It wraps the workload inside an abstract environment called a pod. Kubernetes enforces a strict rule. Every single pod is assigned its own unique routable IP address across a flat network model. Because the network is flat, our tracked query uses this logical topology to navigate directly to the target pod's IP address, bypassing physical server constraints. The application's code binds to an IP and a port, operating without needing to know the details of the underlying physical infrastructure. By enforcing a strict software model, engineers can swap or scale physical hardware without breaking the connectivity of the applications running on top. Our query finally arrives at the AI application's compute layer. Now, the prompt needs semantic processing. Older neural networks, like recurrent neural networks, were limited by sequential processing. They were forced to read data one step at a time, in a specific order. The transformer architecture removed this sequential bottleneck, allowing for massive computational parallelization. Transformers achieve this through an attention mechanism. Rather than following a rigid sequence, attention dynamically routes contextual importance between data points mathematically. The foundational operation of attention translates the input text into three matrices: query, key, and value, preparing them for simultaneous computation. This mathematical kernel calculates attention scores using a dot product between the query and key matrices. This output is scaled by a denominator to maintain variance. Finally, the softmax function normalizes this data into a probability distribution map, identifying the most relevant context. This process links every piece of data to every other piece simultaneously. It creates a logical contextual web rather than following a fixed sequential pathway. This approach to data shares a conceptual foundation with software-defined networking. Both systems abandon fixed pathways in favor of dynamic, calculated routing. Tracing the journey backward, we exit the mathematical matrix, flow back through the logical pods, and pass outward through the identity checkpoints of zero trust. Modern computer science is characterized by the systematic removal of physical constraints. Zero Trust shifted network security away from geographic walls and assigned it to cryptographic identity. Kubernetes and SDN moved network routing away from physical switches and into programmable logic. By replacing physical boundaries and rigid wires with dynamic matrix mathematics, we have built architectures that allow modern compute to scale infinitely.